Well, we've waited long enough, we'll get started. So we'll start with a quick recap of the first law. First law of thermodynamics said if you have a change in the internal energy in the system, it's going to be equal to the amount of heat added to the system minus the work done by the system. And represented as differentials, du is equal to dq minus dw. Right?
Okay.
So let's focus on that dw bit for a second and remind ourselves how we calculate work done by these systems. So here I've got some piston right here. This right here can move. And I've got some gas contained by the piston. And we're going to assume that the gas expands some distance that way, dx. So it expands the piston from here to here.
Okay.
Now there was some pressure outside, like the pressure of the atmosphere, for example, pushing that piston. So as the gas expanded, it had to work against the pressure it was pushing against, right?
Mm-hmm.
And so the force down on it is pressure times area. If you don't remember that, that just comes from the fact that pressure is equal to force divided by area.
There we go.
So that's how we get the force. So now, if the gas expands this amount dx in this piston, then it did some work dw, which is F times dx, right?
Yes.
And force is pressure times area, so pressure times area times dx. And then area times dx gives me my small change in volume right there. Take my cross-sectional area A, multiply it by dx, that gives me my infinitesimal change in volume.
Okay, I see it.
Okay. So that's how we get an infinitesimal change in work. If we want to calculate the total work, we add up all our infinitesimal changes in work.
Okay.
That make sense?
Mm-hmm.
Now I wanted to come back to one of the examples actually before we do that, let's come and populate these table really quick. So we talked about now 4 types of processes that we're going to be dealing with a lot. Isothermal, isobaric, isochoric, and adiabatic. Isothermal meant...
It meant work is equal to 0, or was that isochloric?
Well, just isothermal.
What does iso mean again?
Same temperature. An isothermal...
Oh, temperature is constant.
Right. So an isothermal reaction is one where the temperature doesn't change.
Yes.
An isobaric one is where the pressure doesn't change. Isochoric is where the volume doesn't change. And adiabatic is where no heat is added.
Oh, so W is 0.
No heat is added. Q is 0.
Well, if work is added, then that's adding heat.
Not necessarily.
Oh?
I can do work on a system without adding heat. If I have a piston and I suddenly compress it, I did work on it. There was no heat added to the system. The temperature of the system goes up, so the internal energy goes up.
Okay.
Don't get confused between heat and internal energy. Okay, so really quick, let's calculate work and heat in each of these cases. So let's start by talking about some isothermal case.
Okay.
So the work done, if we're talking about an isothermal reaction, is W is equal to the integral from V1 to V2 of P times dV. Now, it's assumed, in case you were not already making the assumption, we're talking about ideal gases. So PV is equal to nRT, we can always use that.
And since P and V are variables, you want to switch out the P, right?
Right, so I'm going to rewrite P in terms of V here. So P is equal to nRT over V. So that's a dV. So this is equal to the integral from V1 to V2 of nRT dV over V.
Okay.
Replacing the P. Now notice, since we're talking about an isothermal case, temperature is a constant. Temperature is a constant in isothermal reactions. R is just a constant. We're assuming that the amount of gas we're dealing with is a constant. And so nR and T, we can pull all those out.
Mm-hmm.
And so we get nRT times the integral from V1 to V2 of dV over V, right?
Yeah.
And so we calculate that integral, and what do we get? We get nRT times the natural log of V2 minus the natural log of V1, or V2 over V1.
Minus is divided for natural logs?
The difference of the logs, so if I have natural log of A minus natural log of B, that's equal to natural log of A over B.
Oh,
The
I
log
see.
rules.
Yeah.
Another way to think about it is, remember that a log, when you evaluate a log, it gives you an exponent. Taking one exponent minus another exponent is the same as dividing the two numbers.
Yes.
Okay. So logs are done with exponents. Left my eraser over there. Okay, so we recalculated how we get work in isothermal case. This was nRT natural log of V2 over V1. Right?
Mm-hmm.
Okay, let's talk about the isobaric case. So in the isobaric case, we know our pressure is constant, right?
Yeah, so don't you just solve for the integral?
Yeah, so I can just pull the P out and solve the integral. So I get P times the integral from V1 to V2 of dV, which is equal to P times V2 minus V1. So this one's just P times V2 minus V1.
Okay.
And then for an isochoric reaction, where the volume doesn't change,
So your volume's constant.
yeah, so if your volume's constant, what's your work going to be?
Work is 0.
Work is 0 in that case. Because then we're calculating the integral from the same start and end position, which is just 0. Okay, and now, before we talk about the adiabatic process, we need to remind ourselves of one more thing. When we're talking about an ideal gas, when you change the internal energy of a system, that's identical to changing the temperature of the system. So we know when we're talking about an ideal gas, delta U, the change in our internal energy, is always equal to NCV times delta T, change in temperature.
Yes.
Okay. So now if we're thinking about an adiabatic process, the work done in an adiabatic process, so I'm looking for work from this equation, Q minus W. Now if it's an adiabatic process, Q is
Just heat. Or 0.
0, so my delta U is equal to negative my work. Delta U over here is NCV, we'll say T2 minus T1,
Mm-hmm.
is equal to negative work, and so work is equal to, move the negative sign over here, which is the same as just changing the order of these. So if I write this as T1 minus T2, then that's the same as putting a negative out front, right?
Yeah.
And then I can get rid of the negatives on both sides. And so there's my work.
Okay.
Okay? Now let's talk about heat in each of these cases. Heat in an adiabatic case, we already calculated that. That's going to be 0. In an isochoric case, what's heat going to be?
Your negative delta U.
So we're going to have delta U is equal to Q minus work, which is 0.
Oh.
So it's just delta U. So it's going to be NCV times T2 minus T1.
Gotcha.
That's a C, not a parenthesis. Okay. What about an isobaric case? Yeah, so this one's kind of a messier one. So delta U, we know what that is. That's going to be NCV times T2, well, I'll just leave delta T, times delta T is equal to Q minus P of V2 minus V1, right?
Yes.
So when you solve for Q, that's the same as just moving that to the other side. So Q, in this case, is equal to P of V2 minus V1 plus NCV of T2 minus T1. Did I do that right?
Yes.
Okay. And then in an isothermal case, for our isothermal case, since our temperature doesn't change, our internal energy doesn't change. And so I still have delta U is equal to Q minus W. If delta U is equal to 0, and we're looking for Q minus, we know what W is, nRT, or nR natural log of V2 minus V1.
So Q is just equal to that?
So Q is just equal to nR natural log of V2 minus V1.
nRT or nR natural log?
nRT natural log. I just forgot to write it over there.
Okay.
Right? It's the same as the work, basically,
Yes.
in an isothermal case. Okay. So there's our recap from last time. We got tired of waiting for you. Decided to go.
Smart.
Almost our recap from last time. I wanted to readdress this picture from last time and just make it abundantly clear. Because sometimes when I'm up here teaching, I'm so focused on where I know I'm going that I don't stop and think about the questions that you guys were asking. And so I did a terrible job answering this question. And when I went back and rewatched the lecture, I realized just how awful of a job I did. And so I want to answer it right. And so we're going to answer it right. We're going to quickly calculate all these things now. And just make sure that this little cycle here makes perfect sense. So let's re-understand a PV diagram. We're looking at pressure versus volume. Here's all the points at temperature 1. Here's all the points at temperature 2. Temperature 2 is a higher temperature than temperature 1.
Okay.
So we have something going in a cycle. It's going to start at A. It's going to isothermally move to B. It's going to isobarically move to C. And then it's going to isochorically move to A.
Yes.
Right? So we're going to calculate the work done in each case and then the heat added in each case. So going from A to B, what's my work done?
Just your nRT natural log V2 over V1.
Yeah, so it's going to be NR, careful, don't just throw out T willy-nilly, T2, we have that labeled here.
Okay.
So nRT2 times the natural log of our ending volume, which is V sub B, divided by our starting volume, V sub A.
Oh, so we're just plugging in?
Now, since A and C have the same volume, I'm instead just going to call this volume right here always V1, and this volume right here always V2.
Okay.
So it's still V2 over V1.
So in this special case, it happens to be V2 over V1, but I just don't want you to be too in love with that idea.
Okay.
Okay, so there's the work done going from here to here. What's the heat added to the system going from here to here?
The same thing.
The same as the work. So the heat and the work are the exact same in this case. nRT2 natural log of V2 over V1. So not only did the gas do work, but heat was added to the system to keep the temperature the same.
Yes.
Okay, so now comes our compression. Since we're going this way, we're doing work on the gas. And the work done by the gas is going to turn out to be negative.
It's good to, okay.
But yeah, so let's just calculate really quick. What's the work done by the gas? The work done by the gas, we're talking about an isobaric one, is going to be the pressure. Let's also label our pressures here. We'll call this one P1 and this one P2. So it's going to be the pressure, P1, times the ending volume, V1, minus the starting volume, V2. And notice that's going to be a negative number because V1 is smaller than V2.
Yes.
So the work done by the gas is negative going from here to here. What about the heat added to the gas?
It's going to be that same thing.
The heat added to the gas is going to be P1 times V1 minus V2 plus
NCV.
the change in our internal energy, which is going to be our change in temperature. Well, no, I should say it. Our change of our internal energy. I said that right the first time. Of our final temperature. Notice that over here it's the final temperature minus the initial temperature. In our case, our final temperature is T1 and our starting temperature was T2.
Okay, I see it.
So once again, that's going to be a negative number.
Yeah.
So heat was leaving the system even though the system was being compressed.
How does that work?
You stick an ice cube up against it while you're compressing it. Suck heat out somehow.
Well, if you have a piston and let's say you compress it really fast.
We never talk about speed here. There's nothing about speed. We're just compressing it in such a way that the pressure stays constant.
Isn't it like,
So heat has to be leaving it.
didn't you say it was like
That
when
makes
you
sense.
have a little bit of air but it's constantly cooling down because it was really hot and you just push it as it cools down?
Yeah, that's one way to think about it. Heat leaving the system, and so you're pushing at a rate, so as a heat kind of line, but you're basically pushing at the same rate that heat's leaving the system to keep the pressure the same.
Okay, that makes sense.
Which isn't really true because it's actually leaving even more because the temperature is dropping. So it's overcoming the fact that you're doing work on it, and it's still dropping temperature. Okay, anyways, there we go. Now let's talk about C to A. C to A, that's an isochoric action, and so what's the work done?
There isn't any.
0. And then what's the change in heat? Or what's the heat added to the system? It's just a change in internal energy of the system.
Yes.
So it's just going to be NCV times our ending temperature, T2, minus our starting temperature, T1. Okay, so here's all the heat added to the gas. Here's all the work done by the gas. And since this is a cycle, if I take all the heat and I subtract all the work, I should get 0. Because when I go in a full cycle, my internal energy shouldn't change. So if I take all these numbers and I subtract all these numbers, I better get 0.
Okay.
So let's make sure that we see that. So here we have NR T2 natural log V2 V1. Take that, subtract that, so these two cancel each other out, right?
Yeah.
So that cancels with that.
Your pressure cancels out with each other.
This cancels with this, and then this cancels out with itself.
But that's not itself.
These two are negatives of each other. T1 minus T2, T2 minus T1.
And that cancels out.
If I add that to that, that's 0. Add up all my heats. If I would have added up all my Q's, what would I have had? If I would have added up all my Q's, I would have had this. nRT2 natural log of V2 over V1 plus this P1 of V1 minus V2 and then plus NCV T1 minus T2 and then plus this
Yes.
or minus this when I flip the order of these. minus NCV of T1 minus T2.
Oh, I see it.
When you add those two together, that's 0, and then that cancels out the work over there.
Okay.
So when it's all added up, it all comes out 0. That's always the case if it was a cycle. That make sense?
So with these cycles over here, they all have...
We'll worry about those cycles next.
Okay.
One step at a time. I just want to make sure that cycle makes perfect sense, and you feel like you can calculate the heat and the work done anywhere in a cycle like that if I gave you actual numbers.
I think so.
Like pressures and volumes and stuff. Okay. So that finishes our recap. And so now we're ready to start talking about the second law of thermodynamics. The second law of thermodynamics, in short, says that there's processes in this universe that for some reason we can't reverse. We can't undo the process. And so an example is just me taking this book right here. I take my book and I push it and it slides some and stops. So I did work on the book started sliding, the book converted that work ultimately to heat. And so a lot of processes in the universe, we do work to we convert work to heat.
Yes.
We cannot reverse a lot of those processes. And so we call most of those processes non-reversible.
That's original.
That's original.
Mm-hmm.
The processes that we can't reverse are non-reversible processes. Yeah, took a lot of time to come up with that one. Now, we do talk about some processes as being almost reversible, or we pretend that they're almost reversible. And so, let's talk about an example of a basically reversible process, and then one that's obviously not reversible. And the example the author gives is we put a container right here, and the temperature of the container is 0 degrees Celsius. And I have an ice cube right here. With me?
Mm-hmm.
So, for this ice cube, if I had a little bit of heat to the system, then what's going to happen?
It's going to start melting.
The ice cube's going to melt a little bit, and I'm going to convert a little bit of that ice cube to water. And then I can also reverse that by taking a little bit of heat out of the system. And convert that water back to ice.
Okay.
Oh, I see.
With infinitesimal changes in heat. So by taking some other object here, that's 0 degrees Celsius, and bringing it into contact with that thing, and absorbing a little bit of heat or giving a little bit of heat.
Mm-hmm.
And so I can tweak with the ice. What's an example of a process that is completely not reversible, or is not a reversible process? Let's say now I drop an ice cube into a tray that is 90 degrees Celsius. What's going to happen to that ice?
It's going to melt.
It's going to melt. And there's no little fine tweaking I can do to get that ice to unmelt. So that's going to be loosely what we mean by a reversible versus an irreversible process. A reversible process is one that, with a little bit of tweaking, we can get to undo itself. An irreversible process is one where, with a little bit of tweaking, we can't get to undo itself.
That doesn't make sense. That's the same thing you said before.
No, before it was a 0 degrees Celsius thing. So at 0 degrees Celsius, I can get ice to move back and forth between water and ice.
Okay.
At 90 degrees Celsius, I can't do that anymore. The ice is going to turn to water.
Just freeze it and put it to 0 degrees.
You're saying cool down this whole container. But that's not a little tweak to the system. That's a whole lot of energy that I need to somehow suck out of that system. It's not something that could potentially go back and forth. Here's another example of a non-reversible process. A non-reversible process, lighting a stick of TNT. Light the stick of TNT, it explodes. You can't undo that explosion and reassemble the TNT.
Okay.
You can't run that backwards. That's essentially what we mean. It's the difference between processes that you see in a movie versus the processes that you see when you run the movie backwards. When you run the movie backwards, anything you see that seems weird is an irreversible process. I take this chair and I slide it and it eventually comes to a stop. What happened there? I did work on the chair, so that was the energy going into the system. The chair ultimately had friction between it and the floor, so it heated up the floor, caused the atoms in the floor to jiggle more, as it slowly came to a stop. It would be very strange to us if that floor jiggling, all those atoms on the floor jiggling, started knocking the chair in such a way that it started sliding back, speeding up, came back into my hands, and then did work on my arms.
Okay.
And that doesn't really happen in our universe. That would be a reversible process, one that you could undo. One, I'm converting work to heat. A reversible process is where you can undo that and convert the heat back to work.
Mm-hmm.
And for the most part, processes like that don't exist in our universe. We're going to talk about processes where that's almost the case, but not really quite the case. So I'll give you an example of where that's almost the case, but not really quite the case. We think about a piston. There's some gas inside the piston. Now imagine that I was modeling this thing's pressure versus volume. And we'll say it starts out right here. Or we'll say it starts out right here. I'm going to compress it. And I drop a huge block on that thing. So I drop a huge brick right here. What's going to happen?
It'll compress.
It'll compress, but physically what's going to happen is that brick, when I drop it on there, it's going to cause this whole thing to go, and it's going to like wiggle back and forth and slowly come to a nice equilibrium state. You see what I mean?
Mm-hmm.
So at first, it's going to compress it a lot, and so this thing's going to like shoot up like this, and then bounce back something like that, and then, I don't know, scribble, scribble, scribble.
Okay.
And until it finally settles down to some equilibrium state right there. That's not a reversible process.
Is that a pressure volume?
Yeah, this is pressure volume, sorry. So it starts out right there, and instead of it going straight to here, it like shot clear up, something like that. I don't even know if we can keep on one line. I'm not sure if that's the case. Because of everything going on there.
Mm-hmm.
So that thing shoots all over the place. We can't reverse that process. Here's a similar one that we call almost reversible process. It's really close. One that we can reverse would be, I've got this piston now, and instead of dropping a rock on it to compress it, instead I start dropping grains of sand on top of here. One little grain of sand at a time. And as I drop one little grain of sand at a time, then it's slowly going to inch this way, more and more and more and more, right? Now if I want to run it backwards, I just start removing one little grain of sand at a time. And that's going to start running it backwards.
Mm-hmm.
So that's an example of reversible versus irreversible. If I move the piston with something big and sudden, that's not a reversible process. In general, reversible processes are ones that are slow, steady, keeping everything in thermal equilibrium as you go. No sudden changes. And even though we call it reversible, technically it's not completely reversible, because even as I compress that and make it move up and down, there's going to be a teeny bit of friction, stuff like that. So it's not perfectly reversible, but it's as close as we can get. So that's what we mean by reversible versus irreversible processes. Make sense? Now we're very interested in heat engines. Heat engines like what runs your car, like an automobile. And heat engines try to reverse these processes as much as possible. So converting work to heat, that's something that happens all the time. That's real easy.
Yeah.
What's strange is converting heat back to work, reversing the direction of it. That's the thing that's hard to do. And that's what a heat engine is supposed to do. It is trying to run these types of systems backwards. We're trying to, once again, get work from heat.
Okay.
That's the job of a heat engine. That's the job of your car. Your car ignites gas, creates a lot of heat, and somehow we try to get work from that heat. And so one way to state the second law of thermodynamics is that you cannot have a perfect conversion of heat back to work. It's real easy to convert all my work to heat. It's really hard to get all that heat to convert back to work. It's impossible to convert all that heat back to work, in fact. That's one way of stating the second law of thermodynamics.
Okay.
Okay? So let's talk about heat engines then, and give you the basic idea of how a heat engine works. We'll get more fine-tuned to how a car actually works, but just big picture at first for a heat engine and a refrigerator, and then we'll get into more details. So for a heat engine, there's some hot source, some source that has a higher temperature, providing heat to the system.
So it's heating up the system.
Yeah, so it's adding heat to the system.
Okay.
Now, as heat is added to the system, so the thickness of this is meant to quantify how much energy. So this much heat is added. It's pictorial, but
I see.
this much heat is added. Of the this much heat that is added, this much gets converted to work, this much goes to some cold source.
Because heat naturally wants to go to a cooler source.
Because heat naturally will flow from a hot source to a cold source. So we utilize the fact that heat will go from hot to cold to try and get to do some work in the process.
I thought heat just goes up.
No, hot air rises.
Yeah.
That's very different from heat goes up. Heat, if I touch this metal with my hand, what's happening? The metal's temperature is going up, the temperature of my hand is going down, they're achieving thermal equilibrium. Heat is transferring from my hand to the metal.
Mm-hmm.
So that's a flow of heat from my hand to the metal. Now it's really easy to make heat flow and not get any work out of it. So in this case, we're not getting any work out of the fact that heat's flowing from my hand to the metal.
Yeah.
All that heat's being wasted in that sense. So it's real easy to get heat to just flow from a hot source to a cold source. That's real easy to do. The harder part is to try and get some work out of it while it's doing that. And what's impossible is just getting work out of it and none of the heat going towards a cold source. Going into the cold source.
Because the heat will just flow and convert to work.
You can't get heat to just flow and convert to work. In other words, you can't get a picture that just looks like that. Cut off this part. Heat converted to work.
Okay.
That's what the second law of thermodynamics says in a high-level way. If you could get things like that, then you should be able to get this chair suddenly moving back towards me and then does work on me. Convert all that heat back to work. And then I convert the work back to heat, and then the heat suddenly throws the chair back at me, converting all the heat to work. So it's weird processes like the chair suddenly moving that we say that can't happen. And that would be converting heat directly to work. No heat moving towards a cold source.
So in a car engine, what would be this hot source and what would be the cold source?
The hot source, the gas that ignites. And the cold source is the air outside. We'll see specifically a car engine.
Okay.
But high level, that's what it is. Now, we talk about the efficiency of a heat engine. What would you consider an efficient heat engine?
One that can convert as much work as it could.
One that gets a lot of work per unit heat.
Okay.
Right? So, E is just work divided by the heat going into the system.
E for efficiency.
E for efficiency. Yeah, sorry. Not E the number. So if E is equal to work over heat coming into the system, notice that work, we can also calculate work. Work is the amount of heat coming into the system minus the amount of heat leaving the system.
Yes.
Because all this heat goes to that or that, so how much goes to this? This much minus this much gives me this much. You follow that?
Mm-hmm.
So we can also rewrite W as QH minus QC over QH.
You were QC. You wrote OC.
Thank you. And then split this up into two fractions. QH over QH is 1 minus QC over QH.
The author wrote 1 plus QC over QH, or 1 minus.
The author
over I.
drives me nuts because he makes QC a negative value.
Why would you make QC a negative value?
I don't know. So anytime you see me use QC, I may confuse you if I do it how the author does it, because it's just more confusing. So the way that he writes the equation, you'll see he puts absolute values around this.
Yeah, that's what it is.
Okay. We're going to keep these numbers positive so we don't have to worry about the number versus its positive value.
Because if it's Kelvin, it's all positive.
It depends on which direction you want to talk about it. So he wants to talk about the net heat coming into the system always. So he wants to say there's negative QC coming into the system.
That's
I just want it to be understood QH is always going in, QC is going out when you're talking about heat engine. And I'm expecting you to infer things from context.
Okay.
The author, he's trying to make so that you can just plug and chug without having to think. As they do. So this is also equal to 1 minus QC over QH. Two different ways we can write it. And so obviously the efficiency can't be more than
1.
1. Okay, now we also have the notion of a refrigerator. A refrigerator is like a heat engine running backwards. A refrigerator takes heat from a cold source and moves it to a hotter source.
How does it do that?
With some work. You have to plug a refrigerator in. I don't have to plug anything in to get heat to flow from my hand to the metal here. We can get that for free. Getting heat to flow this way comes for free. If I want heat to flow this way, I'm going to have to do some work on the system somehow in order to make that possible.
Yeah, I'm still
Okay.
confused.
Let's give you an example of an actual refrigerator, I guess. So, or we'll do like a AC in a window, just because it's easier to draw. So, we've got, here's you in your room, and in your window you have one of those AC devices, right?
Mm-hmm.
And so this in your room is considered the cold source, and this outside is considered the hot source. And if you've ever gone up to one of these things, you might notice it's blowing hot air out the back,
Yeah.
and it's blowing cold air out the front.
Mm-hmm.
Okay. Now, before we come back to that picture, let me make some observations for you. You ever hook up propane tanks, barbecue, grill?
Mm-hmm.
Yeah, have you ever noticed that as you grill, on the back of the propane tank, you get some frost where it's hooked up?
I haven't noticed that, but I think I've seen.
Or have you felt it at least? Felt the
Yeah.
hookup and felt how it gets
Really
cold?
Mhm.
Why is it getting cold?
I don't know.
The propane gas is really compact in there. And as the propane gas comes out, it's able to expand.
So it makes it really cold?
Well, as it expands, it has to absorb heat. So it takes heat out of its surroundings. Same reason that dry ice is so cold. Dry ice is carbon dioxide in a solid state converting to carbon dioxide in a gaseous state.
Mm-hmm.
In order for it to go from that solid state to a gas state, it has to absorb heat. So it sucks the heat out of the water, that you put it in to make the drink cold really quick. Or you notice that you said when you have to work with dry ice, you have to wear gloves because it'll suck the heat out of you really quick.
Yeah, that's
So if it wants to expand, it has to absorb heat. Furthermore, if you're going to contract it, it needs to give off heat.
okay.
Right?
Yeah.
Or just think about with a gas and piston. We've kind of already talked about this. If I've got gas and piston, and if I push down really fast, the gas heats up. Right?
Mm-hmm.
And if I pull really hard, the gas is getting cooled down inside of there. And so if I pull really hard and the gas cools down, then it will want to absorb heat from the area around it. If I push down really fast and it heats up, the heat's going to want to leave and go to the area around it.
I see.
Okay, so ultimately then what you have inside of here, we have some tube inside of here with some sort of liquid coolant. looping around. I'm trying to do blue and red to help you keep track of when it's which. And then up here, we have it hooked up to a compressor. And then right here, you basically have some regulator that lets it expand once it gets past that point. So we've got some liquid inside this tube here. And the liquid's moving around. This right here is a compressor. So as the liquid moves through there, it gets compressed. This is why you have to plug in an AC. Because you need some sort of motor to actually compress something.
Yeah.
So the liquid flows through here, goes through a compressor. So over here, it's really, really compressed. And so now it wants to give off heat. So over here, the liquid is giving off heat. Because it's been really compressed.
Okay.
So heat flows off of it. You have some air flowing through the system to help get as much heat off of it as you can. So that's why it's blowing hot air out here.
Okay.
And then here's some regulator that once it goes past that, it's able to expand again. So then it comes inside, and now that liquid is able to expand. As it expands, it needs to absorb heat. So it's going to suck heat out of the air around it over here. And then dump it outside, and then etc. Round and round it goes.
I'm just confused how a colder heat wants to go to a hotter heat.
It doesn't.
Well,
Really?
the system right there, that's
Well,
what you're
this
showing.
is a high-level view of this system. We're ignoring the details on how it actually works here.
Okay.
So this is all refrigerators in principle follow this. Here's an example of a refrigerator, even though we call it an air conditioner. It's a refrigerator. It's cooling down the inside, heating up the outside.
So the work you're putting into it is just...
Is
plugging
in
it
compressing.
Gotcha.
All the work is going into compressing the liquid.
Okay.
So the liquid is cooler here. I compress it. So the liquid over here is releasing heat, releasing heat, releasing heat, absorbing heat, absorbing heat, absorbing heat, releasing heat, releasing heat, releasing heat. So it absorbs heat when it's on the inside, releases heat when it's on the outside.
How does the regulator work?
Just lets it expand.
What does that mean?
Doesn't matter. The details don't matter. Just know that it's like you're keeping the guess. I mean, we could use Jeremy to physically do this, right? And the work we're going to do is we're going to actually feed you. And your job over here, you're going to hold two ends of a piston. Your job, you're going to walk into the room. You're going to expand the piston as much as you can, so it's going to absorb heat. Then you're going to walk outside and you're going to compress. As you compress, it heats up, so it lets heat out of the gas. Then you come back in our room and you're going to expand a piston. And so it's going to absorb heat. And you're now acting as our refrigerator.
And that does enough to do what an air conditioner does?
Well, you doing that, no. But it's the same idea, just amped up. So that's what an air conditioner does. That's what your refrigerator does. You'll notice on the back of your refrigerating, there's a bunch of tubes going back and forth.
Yeah.
There's just a liquid in there that's being compressed and then expanded. It's being allowed to expand when it's inside the refrigerator, inside the insulation, and when it's outside, the part that you see, is when it's compressed. And so it's actually hot on the back.
How does air get into the back of the refrigerator?
There's air everywhere. I mean, that's why they have so much tubing, is to give it a lot of surface area.
Okay. that
So a
makes
bunch
sense.
can absorb.
It would work more efficient, like out in the open than against a wall, though, right?
Yeah, somewhat. Not more efficient, but faster.
Faster.
I don't know, I say more efficient.
Because that's our efficient formula.
Yeah, that's a hard one to say. But so yeah, that's ultimately how a refrigerator works. So, sanity question. If we brought a refrigerator in this room and we left it open, would it heat up the room or cool it down?
Wouldn't it heat it up?
A refrigerator?
Refrigerators make it cold.
Yes!
Yeah.
It would heat up the room.
Yeah, but it's the
Because
same
you're
air.
connecting the hot source and the cold
Yeah.
source. So, now that's like saying, well, if we move this inside of here, so now for some reason we're just running our AC and we don't bother sticking the back end out the window because we don't understand how it works. And we think if we just stick that in our room, it will cool down our room. So not only is all the heat that you're eventually pumping out just remixing with your cooled air,
Okay.
but you also have heat as a byproduct of the fact that you're doing work. You're running electric currents. Currents running through wires produces heat.
Yes.
So your work is converting to heat, and your cool air is eventually coming back to heat. And so you're taking this much heat, and you're converting it to this much heat, which is just mixing back into your system. So you're producing more heat. And so if you left an open refrigerator in this room, it would act as a heater for the room, and heat up the room.
Smart.
I don't know about that. But this is one way that you can have heaters and coolers. And so going back to our window, it's not these exact systems, but there are systems like it that essentially, in the summer you have it this way, in the winter you flip it around.
Yeah. That makes
And
sense.
then acts as a heater for you. Okay, so big picture, here's what heat engine is doing. It's converting heat, taking heat from a hot source. Some of it goes to a cold source, some of it is converted into work. A refrigerator, ultimately, is taking heat from a cold source and some work and releasing heat at a hot source.
Okay.
Not the efficiency, I can't remember what it's called, the K there, but it's like the efficiency. What do we want with a refrigerator? We want a lot of QC. We want a lot of heat leaving our cold for only a little bit of work. Does that make sense?
So instead of W
What we
over
care about
QH,
is how much heat we're getting to leave per unit of work we're putting into the system.
Okay.
Can you see that okay?
I can see it okay, yeah.
Okay. And they call that coefficient of performance.
It's not how you spell coefficient.
What?
The K stands for coefficient.
Oh, that's just what they call it. Just a name. Coefficient of performance. QC over W. And now notice in this case, what is W equal to?
Your work is equal to your QC over your K.
No, it's equal to QH, the heat leaving, minus the heat coming in.
That's what it meant.
Because
Over.
QC plus W is QH.
Gotcha.
So W is equal to QH minus QC. So we can also rewrite K as QC over QH minus QC.
Okay.
So that's the other way you'll see it. As QC over QH minus QC. Now, theoretically, what's the biggest K can be?
How is that any different from your E?
What's the biggest E can be?
1.
E can be 1.
What's the biggest K can be?
I would assume 1 as well.
Well, don't assume and just think about it.
Well, you have QC over QH minus 1.
What if my W was really, really small compared to QC? So what if this were really fat and this were really thin? Then what's QC over W?
Just basically QC.
Let's say that QC were 100 and W were 1. What's QC over W?
100.
100. So
So
what's its
okay.
theoretical max?
Infinity.
Infinity. Max here, 1. Max here, infinite.
Why is that?
Well, we just care about different things. What do we care about in a heat engine? We care about how much work we get per heat we put into the system. What do we care about with a refrigerator? We care how much heat we suck out per work that goes into it. It's just what we care about in the two systems.
Okay.
Okay. So that's on a high level what QC and heat engines and refrigerators. So now we're ready to move over and start talking about Carnot cycle. Probably have to pull your table.
Yeah.
Okay, good enough. And get some markers. Okay. So first we'll talk about the Otto cycle, So the Otto cycle, this is actually what goes on inside of your car. The Otto cycle meant to talk about what's happening inside of your car.
Okay.
And so, we're going to start by talking about this process. You start at point A. You're going to go from point A to point B to C, C to D, D to A. And try to describe what happens in each of these states. So, starting at A, notice your piston's volume goes from V to R times V, where R is the ratio your volume increases.
So ratio, so not radius.
Not radius.
Okay.
So R for a standard car, I think, is somewhere around like 8. When your piston expands, so your piston at its most expanded point has 8 times more volume than it does at its most contracted point.
Okay.
Something like that. I'm not sure what those numbers are, but I think it's usually around 8, maybe closer to 10. Anyways, so starting at A, your piston is fully expanded, and it has air inside of it mixed with gas fumes.
Mixed with gas fumes?
Yes, so we allow some gas fumes to mix into the air.
What are gas fumes? Isn't that just air?
No,
Right.
gas fumes, like when you go and you can smell gas, that's fumes going into your nose.
Oh, like gasoline?
Yes, like gasoline.
Okay.
Oh, yes. All of these are gas. Thank you. We're talking about Otto engine. This is actually what's going on inside of a vehicle. So talk about your car. Yes, gasoline. So we have air mixed with gasoline fumes. Starting at point A, piston fully expanded.
Okay.
And then your piston, in the car case, the piston expands and it contracts from the bottom. So then your piston is going to start compressing. So from A to B, your piston started out fully expanded and now it's contracting like that. And it's going to compress the gas together. Compress the air with the gasoline fumes. Good?
Mm-hmm.
And it's going to compress it until it reaches its max compression, some point B. So here's at point B. We have the gas completely compressed now.
Okay.
Now at the top of the piston, that little circle is meant to signify what we call a spark plug. And so when it gets all the way compressed, that triggers a spark plug to go off, which lets off just a little spark, like it sounds. So you have a really compressed gas and you let off a little spark, what's going to happen?
It's going to send an electric pulse.
It'll light up.
It's going to light up. Gas is flammable.
Oh.
Gasoline's flammable.
Okay.
Okay, so there's going to be like a little
Yeah.
mini explosion that happens really quick. Right?
Until, why is it really quick? Why doesn't it just sit there and burn?
It's going to burn up all the gas fumes.
Oh,
It's
I
not
see.
the liquid.
Yeah. Okay.
Oh yeah, it's not like when you have gas and you're burning off the top. It's gas fumes, so all the gas fumes are going to burn very quick, very sudden. So it's like there's a mini explosion, and that mini explosion happens really quick, so it's not like the piston can suddenly expand with it. Piston expanding takes time. This explosion is very quick.
Gotcha.
So the explosion is very quick, and so what that's ultimately going to do is cause a temperature to shoot up inside the piston. It's going to suddenly get really hot.
Yeah.
Okay, so that's what's happening from B to C. This one is a very short interval of time. The gas just explodes, temperature shoots up inside the piston. And now that's at that really high temperature, what's it going to do? It's going to push that piston now with a lot of power back down. So the piston's now going to expand from C to D. And we call that the power stroke. This is where you get all the work out of your piston.
Yeah, which makes your car run. Okay.
Which is ultimately what makes your car run. So from C to D, you have your piston gets pushed to expand. Good?
Mm-hmm.
All right. And then from D to A, what happens is your piston then, at the top of your piston, there's actually two little valves at the top that can open and close. This one is hooked up to your gas fumes, so this is where you can let gas fumes in from. This is hooked up to the air outside.
Okay.
So what happens is, this one's closed off, the piston goes up and pushes all the hot air out, and then we close this one off and let this one open as the piston comes back down, and it lets in air from outside mixed with gas fumes back in.
And that's the exhaust.
And that restarts the system. So ultimately what happens from D to A is we get rid of all the hot air and let cold air back in with gas fumes mixed into it again. And so essentially what happens is the temperature just drops.
Gotcha.
What's the difference between temperature and pressure?
The difference between temperature and pressure.
On a PV chart. Because every time you say pressure and temperature, you can just interchange that.
So looking back to this chart over here, here's all the points at the exact same temperature. Here's all the points at the exact same pressure. Very different things. If you think about an ideal gas, PV equal to nRT, you'll see temperature is related to the product of pressure and volume. So just because the pressure goes up doesn't necessarily mean the temperature goes up, because the volume could have also gone down.
Okay.
Okay. All right. So to make it completely clear, when is heat being added to the system?
When is heat being, when it's compressed?
When it's being lit up.
When it's being lit up. The temperature goes up when it's compressed. That's not heat being added to the system.
Yes.
Right? In a vacuum, I could just compress a gas, expand it, compress a gas, expand it, and it gets hotter and colder, hotter and colder. But there's no heat being added to the system, or heat being removed from the system. I'm just compressing and expanding the gas, changing the temperature. Where heat is added to the system is where it blows up. So QH is coming in right here
Mm-hmm.
when you ignite the gas. When is heat leaving the system?
When you let go of all the hot air.
When we let the hot air out and we replace it with the cooled air and the new gas fumes. So heat leaves the system right here.
Okay, I see.
And then the work we get is the area of this piece right here. So looking back at this little diagram, here's high level how all heat engines work. Here's a particular heat engine.
Okay.
So heat is added to the system. Some of that heat's converted to work. Some of that heat escapes to the cold source.
Do they escape at the same rate?
More heat is added than escapes, because some of the heat had to be converted to work.
And that has to stay in a cycle.
Because the gas also does work. So let's once again fill out one of these tables and then identify QH, QC, and the work done.
Okay.
So going from A to B, what do we have?
An isothermal.
Not isothermal. It's no heat is being added.
So adiabatic.
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 No heat is added.
So adiabatic and isothermal look the same on these guys?
No. It just so happens that I curved it like a temperature line, but a temperature line might be something like running down like this, and then touch it right there finally.
Okay.
So, no, this isn't necessarily isothermal.
I see it.
but it's for sure adiabatic. No heat's being added. So from A to B, we have an adiabatic process. And so what's the work done?
Just
NCVT, change in T.
So we have, let me double check. I think we're going to be doing this as one of the problems here. See if he labels any heats or any temperatures. No, he doesn't. So we'll just use our subscript. Okay. So the work in an adiabatic process, we have the number of moles times CV times our final temperature,
TV.
which is T sub B, minus our initial temperature, T sub A.
Yeah.
Good? And the heat from A to B is
0.
0. Okay, from B to C, what's our work?
It's an isochloric.
Right? So what's our work?
0.
0. There's no change in volume. The gas can't do any work.
Okay.
What's our heat? It's just going to be the change in our internal energy,
Which is
Oh, the same as your work right there.
which is going to be
well, almost the same.
NCV times the temperature at C minus the temperature at B.
Yeah.
Okay? Now, C to D,
Would that also be an adiabatic process?
once again, adiabatic, yep,
Okay.
no heat being added. And so now, it's N times CV times
TD minus TC.
TD minus TC. And then, from D to A, the work we have is 0 once again. And our heat is
NCV
NCV times
TA minus TD.
TA minus TD. Okay. So now, for adiabatic processes, where's my eraser? Over here. Remembering for adiabatic processes, not only did we have the work, but we also had, I'm going to make sure I put the exponent on the right term. I think it's on the V. He doesn't give it as equations in the back. How annoying. Sorry. TVy to the gamma minus 1. Alright, so we know that T1V1 to the gamma minus 1 is equal to T2V2 to the gamma minus 1. So we have that relationship, and we also have, maybe that might be all I need. But for pressure, P1, V1 to the gamma, we also have P1, V1 to the gamma is equal to P2, V2 to the gamma. Okay. So those two hold for adiabatic processes. Our adiabatic processes over here are this one and this one, right?
Okay.
Alright, not sure which substitutions I may do yet. I may have to use that information, just not sure how yet.
Okay.
So give me a sec, I need to play. So when we're calculating the efficiency of our engine over here, the efficiency of our engine, we know, is equal to the work divided by Q sub H, right?
Okay.
Now our work is equal to NCV times the temperature at B minus the temperature at A plus NCV times the temperature at D minus the temperature at C all over Q sub H. Q sub H is, oh, we didn't identify which is which on here. Which one of these is Q sub H?
Your first one.
This one. This is Q sub H, and this one is Q sub C. Right?
Yeah.
This is when the heat is coming into the system. This is when the heat's leaving the system.
How do you know if it's coming in from the equation?
What's bigger, TC or TB?
TC.
So, that's a positive number. What's bigger, TA or TD?
TD.
So this is a negative number.
Okay.
Okay, so QH, we then have NCV times TC minus TB, right?
Can you cancel out your TC and TBs? Why not?
You cancel out.
He's
gonna get an intro to
D's
So you can't factor out the TB from the other side, or the TC from the left.
Oh, because it's adding together? Okay.
Okay, so now we have NCV, NCV, NCV. We can cancel out the NCVs top and bottom.
Yeah.
And so this whole thing then is equal to TB minus TA plus TD minus TC all over TC minus TB, right?
Okay.
Now, using the fact that we know that this is an adiabatic process and this is an adiabatic process, and using this equation here,
Okay.
I'm gonna write some stuff here. I'm basically going to write my TCs and my TBs in terms of TAs and TDs. And you'll see what I mean in a second here. So looking at our first process, that was TB and TA, right?
Yes.
So I know that, using this equation, my temperature at B times my volume at B. What's my volume at B?
V.
It's just V. Don't forget that we had a V down here and an RV.
Mm-hmm.
So my temperature at B times my volume at B to the gamma minus 1 is equal to my temperature at A times my volume at A
Yes.
to the gamma minus 1.
Okay.
Similarly, my
TD and TC.
thank you, TD times, what's my volume at D?
RV.
Oh, so let me do TA here. TA times my volume at A, which is just V.
Why are you doing TA and it's not that? You want to do TC.
Oh, thank you. TC is equal to TD at RV to the gamma minus 1.
Mm-hmm.
So we have both those equations, right? So if I solve this one for TB, then I get TB is equal to TA times R to the gamma minus 1. Because I divide both sides by V to the gamma minus 1.
Yeah, I see it.
And similarly, I'm going to get TC is equal to TD times r to the gamma minus 1.
Are you just gonna plug those in top and bottom then?
Yeah, so I'm just going to do a substitution so that we only have A's and D's, and we don't have B's and C's anymore. So this is now equal to, TB is the same thing as TA times R to the gamma minus 1. And we have minus TA plus TD, that's one we're keeping, minus TC, which is the same thing as TD to the times R to the gamma minus 1. All over, we have
TD times R to the gamma minus 1.
TD times R to the gamma minus 1
Minus TA times
minus
R.
TA times R to the gamma minus 1. Okay. I think we were fine. Okay, so now this is equal to, in the top, we have I'm going to write this as a TD minus TA, those two terms.
Okay.
So we have a TD minus TA. And then we have a TA minus TD to the R gamma minus 1. Or we could do negative TD minus TA times R to the gamma minus 1. We don't need those substitutions anymore.
Yeah, I see.
So we still have negative TD, we still have positive TA to the R times gamma minus 1.
Okay.
All over. I'm going to factor a TD minus TA out of this. So we get TD minus TA times R to the gamma minus 1. You with me? Divide all my terms by TD minus TA. That makes that a 1, that makes that a 1, that makes that a 1. So we get 1 minus R to the gamma minus 1 all over R to the gamma minus 1.
Can't you do 1 minus 1 over R to the gamma minus 1?
I can write this as two separate fractions if you want. So we can also write this as 1 over R to the gamma minus 1 minus 1.
The author wrote it differently.
Then I might have made a mistake somewhere.
No, he did 1 minus 1
Ooh,
over
his
R
top
to
is
the
in a
gamma
different
minus
order
1.
than mine. Messed up a sign somewhere. Let's see. We had. See, I have a TC as a positive. He has TC as a negative.
Why is TC negative?
So from C to D, our work is I'll just skip a mistake. Our work is TC minus TD. Our work in an adiabatic process is the initial temperature minus the final, not the final minus the initial. So I had those in the wrong order, and I have these in the wrong order.
Oh. Gee.
Let's make sure that makes sense. From C to D, we better be doing positive work. So TC is bigger than TD. Okay. From A to B, we better be doing negative work. So TA is smaller than TB. Okay, so now we have it in the right order. So we mixed up our signs on a lot of things. Shoot. What a mess. Alright.
Oh, you're just gonna restart it?
Yeah. We have our substitutions right here, so I'll keep those. And we also know that our NC's are going to cancel out, so I won't bother with that again. So work is going to be, the NCB is going to cancel out. So we have TA minus TB, T sub A minus T sub B, plus T sub C minus T sub D, all over
What about your R's?
TC, I didn't substitute yet, minus TB.
Okay.
I just did work over Q sub H, canceling out all the N times CVs.
Okay.
Now I'll do that substitution. So this is equal to TA stays TA, so we have TA minus B gets converted to
Do
A.
our substitutions still work?
Yes, because it's still an adiabatic process. We didn't mess anything else up.
Okay.
Minus 1 plus TC, which is going to be TD to the R to the gamma minus 1. And then we're going to have minus TD. All over TC, oh wait, not TC, TD times R to the gamma minus 1, minus TA times R to the gamma minus 1. Right?
Yeah.
Okay. So from the top, we can rewrite the top as, I'm going to write that as a TA. Let me do my terms, these terms first. So I'm going to do a TD minus TA. Both those are to the R to the gamma minus 1. So that's this term and this term. And then I'm going to write that as minus TD minus TA, which is the same thing as minus TD plus TA to account for those two terms. Right?
Yeah.
Okay.
And that's all over TD minus TA times R to the gamma minus 1. Now, those all cancel out, leaving a 1 right there. And now that's going to be R to the gamma minus 1, all over R to the gamma minus 1. Or we could also write it as 1 minus 1 over R to the gamma minus 1.
There we
Okay,
go.
much better. It's efficiency can't be more than 1. Okay, some things to note about this then. How can I make my efficiency bigger? I need to make this number over here smaller.
Yes.
How can I make that number smaller?
Lower your gamma.
Well, gamma is kind of a constant of the gas. You can't lower the gamma of the atmosphere.
Okay.
So the other way to do it is to
Smaller R. Bigger R.
bigger R.
Why?
Big R makes small number.
Oh yeah.
So if you had a massive size piston, it would be a lot more effective?
It's not about the size of the piston.
The
It's
ratio.
about its max compression versus its mass expansion.
I thought you said R was a constant.
No, R depends on your piston.
Yeah.
So V is, when your piston is completely compressed, what's your volume? That's V. When it's completely expanded, that's RV.
Yes.
You with me?
You said that was like 8 for a vehicle.
Yeah, it's typically like 8 for a vehicle. So the question becomes, that's dumb. Why don't we just create pistons where with an R of like 100?
Yeah.
Yeah. That's my question.
All right, so that's an actual question. Here's the problem. As you compress a gas, what happens to the gas?
Heats up.
The temperature increases. And as you increase the temperature, the gasoline in there, can suddenly just ignite.
Because it's so hot?
Yes. So what you could have is, as your piston is compressing, the gas just ignites and pushes your piston back before it could even finish its job.
Oh, so it's not even going to start hitting the spark.
Yeah, so the spark plug won't even be used. You're just going to compress it so hard that the gasoline just ignites.
Why is that a problem?
Because then you only get like this far in it, and then suddenly it's pushing back on you. You can completely throw your piston out of whack.
Doesn't it get
Oh,
you
I
past
see.
8 though?
I don't know how far it will get you, but it will be wildly inconsistent, and you're going to have a lot of problems with your engine. It's really hard mechanically to design an engine that at some point it's just going to kick back and you don't know when. Right? Because ultimately your piston is attached to some rotating wheel. There's some rotating wheel pushing your piston up and down.
Mm-hmm.
And you want the piston to push down at a certain point on the wheel. Right? You have that orchestrated. You don't want the wheel to accidentally like kick and go backwards instead of keep going forward and get pushed at the right spot.
Yeah.
So it can create a lot of problems. And that's what they call kickback in a car. Because even in a car, this does sometimes happen.
Where the wheel will just kick back?
Well, no, but where one of your pistons, the gas, combusts early. And so it makes loud booming sounds in a car, and I'm sure you've heard at least in like shows, movies, where you turn on the engine of the car and there's suddenly a those loud booming sounds, that's kickback of the engine. That's occasionally these pistons going off early because it's compressing too fast.
Wouldn't that be really hazardous?
Yes, it's terrible. You don't like that. It's a bad thing for the car. So now, you've also probably noticed that when you go to the gas station, there's a few different options on fuel.
Mm-hmm.
You have your more expensive gasoline and your less expensive gasoline. Your more expensive gasoline is gasoline that it takes a higher compression to get to instantly combust. So your more expensive gasoline is gasoline that is more guaranteed to not pre-combust.
Oh, I see.
And so your more expensive gasoline, you can put in engines that have higher R values there.
Okay.
And so if you're driving something like a sports car, you probably want to use nicer gasoline to make sure that there's no kickback.
Yeah.
Oh, I see.
But if you're driving a little two-piston car, then you're fine with the cheap stuff. And so that's what the different gasolines are. Now, there's also one more type of gasoline at the pump.
Yes.
Diesel. Right?
What is diesel?
Yeah, what's a diesel? What's this diesel stuff? So, now let's talk about a diesel engine.
Oh.
Because a diesel engine actually works different from a regular car engine, and diesel engines are more efficient. So how does a diesel engine work? It's almost identical to the way a car engine works. It's going this way. Almost identical with one big difference. So the diesel, when you start compressing it, there's no gasoline in there. So it gets to its completely compressed state without any gasoline. And then on a diesel engine, you have what's called an injector. And so there's an injector then, which when it's completely compressed, injects diesel fuel into the piston. So completely compress the gas, and we start injecting diesel fuel into the engine. And it's so compressed that as that gas is being put into the engine, it's instantly combusting. So this is their way of getting around that problem. They say, if we don't want the gas to randomly compress, or randomly go off while we're compressing, let's just compress without any gasoline in there. And then we'll put the gasoline in after it's compressed.
Oh.
Okay.
So then they inject the gasoline. As they inject the gasoline, it instantly combusts as it's being put in, which starts the piston expanding. So the piston starts expanding from us inserting gasoline in there. We did our injection, it expanded that much. That's enough. Now we let it finish expanding the rest away. And then it goes through the same cycle of release the hot air, suck back in cold air, compress, inject the gasoline, let it finish expanding, etc. That's the difference between a diesel engine and a regular engine, how their pistons work. And so, diesel engines are more efficient. You can get R's of like closer to 12 or 13 with the diesel engine, much more efficient. But they're also more maintenance. It's a lot harder to design something that can inject fuel into the piston at those high pressures than to just let gas already be in there.
Oh,
So
I
you're
see.
trading off efficiency with complication. So it's a more complicated engine, but it's also a more efficient engine. And so that's your back and forth trade-off there.
So what's wrong with the diesel fuel in that car?
So diesel fuel, I'm not positive what makes it different. Other than it's designed for diesels. I'm sure there's like some nice combustion range that they like for diesels that isn't great for cars. I don't know if it's more or less or what it is.
Okay.
Maybe diesel can be like even extra flammable. And maybe that makes it you can get more out of it when you burn it. I'm not sure the chemistry behind it. So yeah, I'm not positive. I just know with regular cars the difference between those gases.
Yeah. Is it the same kind of difference where it just affects the R? Or because they don't have to worry about compressing with the gas, it'll just ignites immediately?
It's a big part of it. From a buyer's perspective, that's the greatest difference. Okay. So now, briefly summarizing the second law up to this point, we can summarize the second law up to this point with these two pictures. The second law of thermodynamics says these two pictures are impossible.
Yeah, that makes sense.
Picture number one, you can't convert all your heat to work without any heat going to your cold source. Picture number two, you can't just have heat flow from your cold source to your hot source with no work coming in.
Yeah.
The question for us is what is theoretically the most efficient engine it is possible to build? So this has an efficiency of 1 minus 1 over R to the gamma minus 1. And this was ignoring all friction. And so at the end of the day, your cars have about a 30% efficiency. About 30% of the gasoline that you put into your car is actually being converted into getting the car to move. The rest of it is lost to heat.
Yeah.
Wow.
So the question is, theoretically, what is the best efficiency we could possibly achieve for a heat engine? And so that engine that we're going to talk about is what the Carnot cycle is meant to reproduce. Now I want to read one paragraph that the author had to say to help make sense out of the fact that a Carnot cycle, well, first I'll give my 2 cents and I'll read what the author says. You're going to notice that the Carnot cycle only uses reversible processes.
Okay.
Because that is what a heat engine is trying to do. So what happens for free is converting work to heat. That's easy. I pushed the chair. I converted work to heat, ultimately in friction. That happens all the time. What we're trying to do with a heat engine is reverse that process and convert heat back to work. That's the whole goal with a heat engine. So let me read what the author says on this. To understand the rationale of the Carnot cycle, we return to reversibility and its relationship to directions of thermodynamic processes. Conversion of work to heat is an irreversible process. The purpose of a heat engine is a partial reversal of this process. The conversion of heat to work with as great an efficiency as possible. For maximum heat engine efficiency, therefore, we must avoid all irreversible processes.
We must avoid them.
must avoid irreversible processes, or we must use reversible processes. So we're only going to use reversible processes.
Okay.
To get our theoretically most efficient heat engine, we need to use only reversible processes.
That makes sense.
Okay. So here we have the Carnot cycle. And this is not meant to design an engine used in a car. This would be terrible for an engine used in a car. It's just an engine that's supposed to be very efficient. Not necessarily give you a lot of energy really quick. It's just the energy it gives you, it will give it to you efficiently. Okay, so how does a Carnot cycle work? Start at some point A, and we're going to isothermally go from point A to point B, and then adiabatically go from point B to point C, and then isothermally go from point C to point D, and then adiabatically go from point D to point A.
Okay.
So we have no sudden explosions going on here, like the gasoline igniting, and we have no suddenly just getting rid of all our hot air going on here, like we did at the end of each of these cycles.
Yeah.
Those would be irreversible. Once you release hot air, you can't recapture the hot air. It's gone.
Okay.
So we're only using isothermal and adiabatic processes.
Okay.
Okay, so let's calculate the work done and the heat that goes into each part of this cycle. So from A to B, what is the work that we do?
Just nRT. Well, nRT2.
nRT2 times the natural log of our final volume over our initial volume, right?
Mm-hmm.
So that's the work done going from A to B. What about the heat added to the system going from A to B?
The same thing.
0. Oh, sorry. Same thing. nRT2 times natural log VB over VA. So isothermally going from A to B. We did work, or the gas did work, and so heat had to be added to the system. Because it's staying the exact same temperature, so its internal temperature, or its internal energy of the gas is staying the same.
Okay.
All right, B to C, now this is the adiabatic process. What's the work done going from B to C adiabatically?
NCV change in temperature.
Mm-hmm.
So we have NCV, NCV times
Your initial minus
our
your
initial
final.
minus our final. So our initial temperature is T2 minus our final temperature is T1.
Okay.
Okay? The heat added going from B to C.
Now that's 0.
Now that's 0. From C to D, once again, this is isothermal. So this is just going to be nRT1 times the natural log of, remember, our final minus our initial. So VD over VC,
Yeah.
which is going to be a negative number. It's doing negative work.
Okay.
Because VD is smaller than VC.
That makes sense.
No. VD is bigger.
I have no clue why I wrote it like that. This is pressure. This is volume. Sorry.
Okay.
Good eye. So weird. I didn't do that anywhere else, right?
Well,
Just that one? Yeah, okay. That was weird. Anyways, and then this over here, same thing. nRT1 times natural log T1 times natural log of VD over VC. And so once again, heat is leaving the system as it goes from there to there.
Okay.
And then finally, D to A.
Just switch your temperatures around.
D to A, we have NCV, and then we have our
Initial minus your final.
initial minus our final, and the amount of heat added to the system is 0. So the work done by the gas here is negative, so we did work on the gas going from D to A, which is why the temperature went up. And my picture is terrible. From D to A, we should have compressed it a lot,
Okay.
which my picture doesn't make very clear.
Compress the volume.
Yeah, there should be a bigger gap in the change of volume from here to here. This should be more stretched out. Okay, so my picture's lying to you, but I think our table here is correct. Okay, so now let's calculate our efficiency. So once again, E is equal to our work divided by the heat that comes into the system. Right?
Mm-hmm.
Why is it that and not the other one, like the refrigerator?
Because we're running a heat engine.
A Carnot cycle was a heat engine?
Well, if we run it backwards, it'd be running like a refrigerator. But right now, we're converting heat into work. We're getting work out of the system. We're not putting work into the system.
Okay.
So this area here, when we go this way, come down, then our work is this area here.
Gotcha.
So we have work over QH, where our work is all those. Let's see, let's identify our QH really quick. QH is when heat is coming into the system. Is heat coming into the system here?
Yes.
Yes. So here's our QH. Which means here, heat better be leaving the system, right?
Mm-hmm.
Yes. So here's our QC. Okay. And let's see how he's doing this so I don't make a mess. Oh, he's going to calculate this, which is smarter. We could do it as work over QH, or we can do 1 minus QC over QH.
Yeah, I like that.
And that's simpler, so we don't have to deal with the work, because the work's kind of a lot in this one. Right?
Yes.
Okay, so let's look at QC over QH then. So QC over QH, focus on that part, is going to be this over this. So nRT2 times the natural log of VB
That's QH.
over VA. Oh. Thank you. nRT1 natural log of VD over VC all over nRT2 natural log of VB over VA.
Can I interrupt you?
Go ahead.
Intuitively, don't you want QC over QH to be super small to get the most effective system?
Yes.
Okay.
Okay, so this simplifies to n's cancel out, r's cancel out. Let's know something about the logs. So B to C was an adiabatic process,
And D to A.
and D to A was an adiabatic process. So, looking at these relationships for adiabatic processes, from B to C, not sure which one of those are better to use. Maybe it doesn't matter. They both have a warning, so I don't know that matters. We'll use this one, because why not? Okay, so using the top one, and we were talking about B to C, right?
Yes.
So B to C, so we have the temperature at B, which is T2, times the volume at B, to the gamma minus 1, is equal to the temperature at C, which is T1, times the volume at C, which is VC gamma minus 1, right?
Okay.
Now looking from D to A, that one was also adiabatic. So the temperature at A times the volume at A is equal to the temperature at C, D, thank you, temperature at D times the volume at D. Alright, those are correct, right?
I think so.
So now notice, since this is equal to this, and this is equal to this, then this over this is equal to this over this. You see that?
Mm-hmm.
And so our temperatures cancel out. T2s cancel out with T2, T1 cancels out with T1. And so we're left with VB over VA to the gamma minus 1 is equal to VC over VD to the gamma minus 1.
No, VD over VC. Oh no, you have that right.
VC over VD
But
to the gamma minus 1.
over there, your top one is VD over VC, but your bottom one's VB over VA. Does
Okay.
that have to do with that?
We'll get there.
Okay.
Alright, so now we can cancel those out, and so notice that VB over VA is equal to VC over VD. Right?
Mm-hmm.
And so, when I derived this equation for you, I made so that QC was always a positive value.
Mm-hmm.
Now you're going to switch back?
No, I'm not going to switch back. It's just what we called QC here wasn't really this value. This value was negative QC. Because this is a negative value.
So you have to switch around your log?
So when I did QC over QH is equal to this, I really just need a minus sign in here as well.
I see.
So QC over QH is equal to negative, those canceled out, so we have T1 natural log of VD over VC, all over T2 natural log of VB over VA, right?
Yep.
Rules from our logs, I can take any coefficient and put it as an exponent, so this is VD over VC to negative 1, which flips their reciprocal.
So it's VC.
So it's VC over VD, natural log of VC over VD. Since VB over VA is VC over VD, their natural logs are the same, so those cancel out, and the negative moved up there. So we get QC over QH is equal to T1 over T2.
T1's an exponent.
T1's not an exponent. We left the exponent, we just moved the negative 1.
Oh.
Good. Okay, and so there we have our efficiency. E is equal to 1 minus T1 over T2. And that is your maximum possible efficiency, where T1 is the temperature of your cold source and T2 is the temperature of your hot source. This is your max theoretical efficiency. You can't be more efficient than that with a heat engine.
So you want...
So with a car's engine, essentially, the hotter the fuel you're exploding and the colder it is outside, the higher your maximum possible efficiency. And to get a perfect efficiency of 1 would require your cold source to be absolute 0.
Which isn't possible.
Which you can't have. So there's no such thing as a 100% efficient engine like this.
Less electric.
No. Alright. Yeah, no, electric doesn't help. Okay. So, since all these processes were completely reversible, we can run all these arrows in the exact opposite direction. So we can run it this way, this way, this way, and this way. And now we're using work to move heat from a hot source to a cold source. And now it's running a refrigerator rather than a heat engine. You with me?
Is the efficiency still the same, or wouldn't you use
Well,
that?
now we'll calculate K.
Oh, I see. Okay.
So what is K equal to? Well, K, notice, is equal to QC over QH minus QC, right?
Wouldn't that change some of the orders of T2s and T1s and VDs and VCs?
Sure. But it won't change yes, it will change the orders on things, but it won't change the ratios.
Okay.
So this ratio would still come out the same. Because when you flip that, you flip that as well.
Oh, that makes sense.
Okay. So QC over QH minus QC is the same thing as QC over QH divided by QC, oh no, I did that right, over QH, divided by QH over QH minus QC over QH. You with me?
Oh yeah, I see it.
Which is equal to QC over QH then is going to have this ratio, same ratio as T1 over T2. So T1 over T2 divided by, that's going to be 1.
Mm-hmm.
I can rewrite 1 as T2 over T2. No reason I can't, right?
Yeah, okay.
Minus QC over QH is the same thing as T1 over T2. And then that's equal to, divide all my terms by T2, and we get T1 over T2 minus T1. And so, the max heat flow we can get from a cold source to a hot source per unit of energy happens when our hot source and our cold source are the same temperature. As long as your hot source and your cold source are the same temperature, it's real easy to make the heat flow between the hot source and the cold source, is what that tells us.
Yeah, but that's
Surprise, surprise.
not effective at all, right?
No. But the max efficiency we can get depends on the temperatures, is all it's saying.
Okay, I see.
So you can't achieve a perfect efficiency with a refrigerator unless they're the exact same temperature.
It's kind of fun.
Okay. So now I told you that the Carnot cycle is the most efficient cycle possible.
Yes.
And the Carnot refrigerator is the most efficient refrigerator possible since it's just running the Carnot cycle in reverse. And I told you some stuff about, well, since we only use reversible processes, blah, 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 you're probably not still convinced.
Okay.
Which I would expect you not to really be convinced.
Yeah.
Okay. So now I'm going to give you a nice little pictorial proof of this, after which I think you'll be convinced. You'll be convinced if you accept that this is impossible.
Yeah.
Okay. Then I can convince you. So we're going to start off with, I'm taking a Carnot heat engine and I'm putting it right next to a Carnot refrigerator. So here's my Carnot heat engine.
Yeah.
Here's my Carnot refrigerator.
Okay, I see it.
And I'm going to plug my refrigerator into my engine. So the work it spits out here goes straight into that. And so now we're just going to be cycling forever. So far, right?
Yeah, that makes makes sense.
This is pumping heat up to our hot source. It then takes that heat, does some work, and pumps it down to our cold source. We pump that cold source back up with the same work to our heat source. And it's no surprise that we're able to do this because it was completely reversible processes. Right?
Mm-hmm.
Now let's assume that for some reason, somehow, with some crazy technique, using some sort of crazy quantum mechanics and whatever, you were able to make an engine slightly more efficient than the Carnot engine. You're able to come up with one that's just slightly more efficient.
Okay.
So that means when you add just a little bit more heat here, so when you do Q sub H plus some teeny extra bit, then you're able to get just an extra bit of work out of it. So you're able to get W plus dW work out of it.
Yes.
You with me? Now notice that we only need W to keep our refrigerator running.
Yeah, but that doesn't.
So we have dW extra.
No, because then when you pump it through, you don't have enough extra dQ.
So we have W dW, W goes in there, and then out of the whole system we have, here comes dW coming out of the whole system. You with me? So ultimately, what is this whole system doing? It's taking dQ and it's converting it into dW coming out of the system.
Where's the dQ coming from?
Our hot source.
It's just pumping in extra somehow?
Our hot source has as much hot as you want. That's what we assume. When we look at this, when we look at those pictures, our hot source just has a bunch of hot. Has as much heat as you want.
But it can only pump out the same that's been pumped in.
No, we're just moving heat out of our heat source.
Well, then your heat source is eventually going to not be.
It's eventually going to, that's fine. But notice what's happening. Ultimately, our heat source is losing a grand total of dQ heat.
Every cycle.
And where is it going?
dW.
It's going into work. It's not going to a cold source.
Okay.
We have dQ going to dW, not going to a cold source.
But that's not possible.
But that's not possible. So this can't exist.
Well, yeah, it makes sense.
So if I create a slightly more efficient engine, then I'm able to convert heat directly to work.
Won't that just make more heat?
Make more heat.
Like, won't the dW just go to making more heat?
No, the dW, I can then use it to do something like power a light bulb.
Yeah, that makes sense.
Okay.
So now I have a machine that is converting heat and powering the light bulb. As long as I make sure it has an infinite supply of heat, I can get as much work out of it as I want. Directly to work. Because everything that went to the cold source ultimately gets back up here.
How do you know that dQ just goes to work though?
Where else can it go? dQH goes to W and QC.
Mm-hmm.
So dQ goes to dW.
Why doesn't dQ get split in half and half of it goes to cold and half of it goes to dW?
Because then it wouldn't have been a more efficient engine. We said, let's assume that we can make one slightly more efficient.
Okay.
Just a teeny bit more efficient.
Which would pump out
So
more
when
work.
you give it an infinitesimal more heat, then it gives infinitesimal more work than a regular Carnot engine.
But that's not possible.
And we're showing that's impossible. Because
Oh.
then you
Oh,
can take
I
a
see
Carnot
what you're
engine,
doing. Okay.
you can take your impossible engine, connect it with a Carnot refrigerator, and together, all wrapped up in one package, they essentially do this.
Yes.
Which is impossible.
Yes.
So you can't have an engine more efficient than the Carnot engine. You can't beat the Carnot cycle.
Okay, that makes sense.
Doesn't matter what crazy physics you come up with, what crazy ideas you have, what materials you're working with, you can't beat it. Because otherwise you could do something like this, which isn't possible. Because that's doing this, which is impossible. Right?
Yeah.
Okay, well, unfortunately, we'll probably have to end it there for today. So tomorrow we'll go over all the example problems up to this point and then cover entropy, which will be the very end of everything, and we're done.
So entropy ends it all.
Entropy ends it all.
The measurement of chaos ends it all.